In this video we're going to look at the area under a curve, and what it actually means when it says under a curve is the area that's between the curve and the x-axis. So I've got a couple of pictures down here. So here's a piece of a curve, and the area under the curve that we're talking about is the area that's contained between these two blue lines, the curve and the x-axis, so this funny shaped thing here. So to find the area under the curve, what you can do is you could put your curve onto some grid paper and count the squares, like you did in primary school finding the area. You can use the formula for shapes that you already know. So for example, we could do this area under the curve here. We could do an approximate area by using this particular rectangle here. So we can find this distance, this height, and we can find the area, and then we could approximate this with a triangle if you like. So just using different known shapes and combining those areas together. So if we just use this blue rectangle sitting underneath this curve here, you can see that that blue rectangle is actually less than the actual area that's under the curve. And if we used a rectangle that encompassed the whole of the shape, like this green rectangle here that's all across this where the green lines are, you can see that the actual area that's under the curve is less than the green area, which is this big whole thing here, but more than this blue area. So with this green one, we've actually estimated more, so it's somewhere in between the two. So let's have a look in a little bit more detail about how we get this as accurate as possible. So we're going to stick with using rectangles. They're the most common things that we use. So we're going to approximate the area using rectangles. And so we're going to try and approximate the area under the curve that I've got here between x is equal to 2. So this is x is equal to 2 here. It might be a little bit hard to see. No, actually, I've got that as x is equal to 1. So I'll change that. That's better. And x is equal to 6. So we're looking between this line here and x is equal to 6, this line here. So we're going to use rectangles to try and find the area under specifically this piece of curve here. Now we're going to use two sorts of rectangles. You can see here we've got what we call left end point or left end rectangles. Sometimes they call them left rectangles. And left rectangles have their top left corner touching the curve. So you can see that this one here, top left corner touching the curve. This one here, next one along, top left hand corner touching the curve. So these are left rectangles or left end point rectangles. And over here I've got right end rectangles. So if I look at this rectangle over here, you can see that the right hand side in the top corner is touching the rectangle. The next one across, right hand corner touching. And you can see for each of the triangles, each of the rectangles I've got here, it's the right hand side that's touching. And what you'll notice is that all of my rectangles are the same width, so the width is always 1 unit for both of these when I'm comparing them. So from 1 to 2, 2 to 3, 1 to 2, 2 to 3. Now, to find the area under the curve, I add the area of all of these rectangles together. And for the left end rectangles, the actual area that I get from my rectangles will be less than the actual area under the curve, because you can see that it's actually missing little bits here. So this will be an underestimate. On the right hand side, with the right hand rectangles, you can see that each of the rectangles includes a little bit more than we need, so it's going to be an overestimate. You'll also notice that for left rectangles, I used all left rectangles, and for right rectangles I used all right end rectangles. You don't mix them up. So let's have a look at some other rectangles. Just move this up. we've got lower rectangles and upper rectangles. Oops, move up a little bit more. So in this one we're going to do lower rectangles, and what that means is that again we're going to go between 1 and 6, that all of the rectangles sit underneath the curve, and that the height of the rectangle is determined by whichever side of the rectangle touches the curve first. So for example, if I draw a rectangle along these two lines here, you can see that there's 2 points where this rectangle touches the curve here, or where that's 2 green lines touch the curve here and here. This one is the lower of the two, so we create our rectangle there. And what you'll notice is that sometimes with lower rectangles you'll get left rectangles, and sometimes you'll get right rectangles, depending on the curvature of the curve. On the other side here, we have got upper rectangles. So in this version we've got upper rectangles. So the same idea, we draw our 2 lines for the sides of the rectangle, just draw all these columns, and again you can see that this column touches the curve at this point and this point. If we're doing upper rectangles, we choose the top point here. And so what you'll end up with in this case is columns that look like this. Oh, it's that little column sitting up there. And again, some of these rectangles will be taller than the curve. Actually, they're all taller than the curve, but some of them will be left-hand side and some of them will be right-hand side, depending on the curvature of, the curvature of the curve. Now, one of the common mistakes people make is that they think that if you're doing lower rectangles or left rectangles, you always get lower rectangles, and that's absolutely not the case, as you can see here. It depends on the curvature of the curve, whether it's increasing or it's decreasing. If you're using left and right rectangles, you'll get different approximations, but the point is you need to stick with whatever it is at the top. Okay, so different types of rectangles will give you either an underestimate of the actual area. So the lower rectangles at the minute are giving us an underestimate. We're missing all of these little sections of area as well, or they'll give you an overestimate. So our upper is giving us more area than what we need. And whether that's an overestimate or an underestimate will depend on the shape of the curve. Being able to get the best estimate or best approximation for the area under the curve, what we can do is we can remove as much under or overestimate as possible. So you can see that I've got 2 different setups here for the area between 2 and 5. Area between 2 and 5, and this is in fact the same function. And what I've done on this side, I've used 3 rectangles to estimate the area under the curve, and that leaves this amount here. All of those sections are all going to be underneath the area that we need. And on this second one here on the right, I've used much smaller rectangles, and so I get a lot less area that I am missing. So to find the area of each, to find the total area, what I do is I find the width of this rectangle, which is 1, and I find the height of this rectangle, which I can read from here as being 0.8, and so I find the area of this one, and I add it to the area of this one, which will be 1, because that's the width, times 1.8, so that's 1.8, And if I do the last rectangle as well, add them all together, I get 5.8 units. So I'm going to do the same thing here, but this time my width is 0.5. And so I've got a lot more rectangles to calculate. So it's going to be 0.5 times this height, 0.5 times this height. So I'll go ahead and I'll put the values in here, and then we'll see what our area is. And as you can see, I've had to do a lot more calculations of the areas, but the area that I end up with at the end is 6.9 units, and that is a much better approximation than the area that I had before. And so to get a more accurate approximation, we put more rectangles. Let's have a look at that in a little bit more detail using this activity here. If you want to look at this and play with this yourself, you can see that I've left the URL up here for you. So we generally refer to these sums as what we call Reimann sums. You can see it's here. And what I've got here is a curve y equals x squared, so there's our curve here. I've turned our rectangles on. The other thing I want to turn on is the actual area. So you can see that the actual area under the curve here is 9, and I have the triangles, the rectangles set as being the left-hand rectangles. And so what it's actually doing here to find the Reimann sum is the sum of all of the rectangles. So this value here is the sum of all of these rectangles all together. And so I can actually move from left rectangles to, come on, work for me. If I slide this slider, middle rectangles to, there we go, middle rectangle. So you can have the middle of your rectangle as your measurement. And you can see that you get a different value for the sum up the top in blue. So our left sum was 7.8. Our middle sum was 8.9 and our right sum was 10. And so you can see that our right hand side for this curve is an overestimate. We've got area sitting at the top. In the middle we kind of get a really good approximation of it, and then on the left we've got an underestimate. So I might just leave it sitting in the middle just for fun. So watch what happens. Now remember, our actual area is 9. So what I'm going to do is I'm going to increase the number of rectangles now using this slider on the bottom. So you can see that the number of rectangles here is 3. I'm a bit away from the area, and as I increase the number of rectangles, you can see that I'm getting closer and closer and closer to the actual area. So what I want to do is try and put in as many rectangles as possible. And unfortunately that means lots and lots of calculations. So maybe we can find a better way to do this. But before we find a better way to do this, you have to be able to do this by hand. And so that's what I'm going to show you how to do now. So to find, I'm going to pause this video and let you read through the instructions, and then I'm going to show you how you go about finding the area below this curve for 0 to 7 using lower rectangles of width 1 unit. So I'll let you go ahead and read these instructions here. Okay, so here we go. First step, I'm going to divide the x-axis into sections of equal width. So my question told me they had to be width of 1 unit, so that's what I've done here. Second step, I'm going to add vertical lines from the x-axis to the curve for each side of my little stick. So I should have a little stick sitting here, so I'll go ahead and do that. So there's all my vertical lines, and these first 2 steps are the same regardless of the sorts of rectangles that you're going to use. So now I'm going to do step 3. I'm going to complete the rectangles based on the type of rectangle that I've been told to use. And in my question, I'm told to use lower rectangles. So I'm going to have a look at the first section where a rectangle is going to be, and I'm going to take the lowest point on either the left hand side or the right hand side. So I have 2 points to choose from this one. This point here where the green vertical line cuts the curve, and this point here where this green vertical line cuts the curve. So to make a rectangle using the lower of those two, I actually draw a line at the bottom. And this is part of the thing that gets people confused. It is possible to have a rectangle with no area. You just have to follow the process. So now I'm going to move on to the next rectangle, and I consider both sides. So I have a point here and I have a point here. I take the lower of the two, the one with the lower y value, so I'm going to use this side, and so my rectangle becomes here. For the next column, I consider this side and this side. This one is the lowest, so I put a line across here. Next column, I consider this point and this point. They're actually the same because it's symmetric. This is an inverted parabola. So take that line there. For the next column, I consider this point, which is on that side, and this point, which is on this side. So this is the lower of the two from between this one and this one. So I'm going to put a line across here, and so on and so on. And you'll see that what we end up with is a couple of rectangles that actually have no area. So we've got a rectangle here, 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 here. These are the areas we work out, and we include, most importantly, we absolutely include this area here that has a 0 and this area here that has a 0. So always, always, when you're making your rectangles, start from the left-hand side and follow the rule. So finally, I need to find the area of each of these rectangles. So for the area of the first rectangle, we have 0. For the area of the second rectangle, it is 1 unit wide by 2 units high, so that's a 2. Our next rectangle, 1 unit wide by 3 units high, so that's a 3. Our next one is 1 unit wide by 3.5, 3.6, and so on and so on, and a 0. So we add all of those together to make our area. And if we do that, we get an area of 13.6, including, oops, and I haven't got it on there, including both of the zeros that we had on the end for our empty rectangles. Don't forget that you need to add those in. All right, so what do you do if your function is a function and you don't have it drawn on a graph where you can read across from the y value? You need to do some substitution. So let's have a look at that. So for this one, we're going to estimate the area enclosed by the curve y equals x squared plus 1. And that should say, and the x-axis between x is equal to -2 and x is equal to 2, using first left rectangles of width 0.5 and then lower rectangles of width 0.5. So the questions, if they ask you to do this, will tell you the two, what we call end points, the lower end and the upper end, the sorts of rectangles to find and how wide they are. So here's a graph of x squared plus 1, and so I've got it sitting over -2 to 2, which is what we're meant to do. So I'm going to go ahead and I'm going to divide this up into widths of 0.5 units. So I'm going to use the step from before. So I'll go ahead and do that, and then I'll put my columns in, and then we'll go from there. Okay, so you can see that I've got them at 0.5 widths, and the lines are kind of straight. They're a little bit wonky. So I've been asked to do, for these ones, I've been asked to do, for the first one, left rectangle. So I'm going to go along each of the columns and take the left-hand side and make a rectangle from it. So the first rectangle sits there, the second rectangle sits from that point, etc., etc., etc. And so to find the area of this particular rectangle, the first rectangle, I'm going to need to know what that height is there. And to find that height, what I need to do is I need to substitute -2 into the equation x squared plus 1. So if I let x squared plus 1 be f of x, so let f of x be equal to x squared plus 1, then the area of this first rectangle is going to be its height, which is f of -2, times by its width, which is 0.5. And then I go through and I do the next rectangle using f of -1.5, etc., etc., etc. And so what I've got is a particular type of pattern, and you can see it here. Each time multiplying by 0.5. So one of the things that you can actually do is that you can simplify it by taking out the 0.5 as a common factor and then just adding all of your substitutions together, which is what I've done here. So instead of writing f of -2 times 0.5 plus f of -1.5 times 0.5, etc., 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 I've just got all of those values added together and then finally multiplied by 0.5. Now, you need to be very careful. Left rectangles are fine, and you can see that it's definitely a pattern here in the x values going up by 0.5 each time. But that's not always the case. So just double check with your picture to make sure that you've got the right values here. So I'm not going to work that out by hand. What I'm going to do is I'm going to get my CAS calculator to do it for me. So let me just move this out the way. So here's my CAS calculator. I've defined the function, and then I've asked it to find, and you'll notice this, it's a little bit weird, but I've asked it to find the sum of f of x, given that x is each of these values in turn. So you'll notice that I've got the curved brackets for the set of values, and I have a comma in between each one. And what the CAS calculator will do is it will substitute each of these numbers into f of x one at a time, and it will find the sum of them. So it's literally going to do this for me. And that gives me 0.19 as my answer, as the sum of all of those functions. And I've got a mistake here. I'll just fix this up. So what our actual answer will be, it will be 0.5 times that value, because this bit here just finds the value of that big bracket there. So my actual answer is going to be times by 0.5 square units. So that's going to be 9.5 square units. And square units, or just units, is generally the units that you use, units of area that you use for these questions. So let's have a look at the next one. And this time we're doing lower rectangles. So let's just move this out of the way. There's our picture. And again, we're going to do lower rectangles. So I'll go ahead and fill in the information for this question for us. So I've put my lines in, and I've chosen the lower one for each. And this time you can see that the first few rectangles have the right hand side point, and then the other ones on the positive section where it starts to curve up have the left hand side. So that's going to make a difference in our pattern. Remember, I talked about the pattern here and watching the pattern here. That's going to make a difference in the pattern of what we actually get. So our first couple are f of -1.5, which is this first one, and then f of minus 1 for the second one, both times 0.5. We'll do the same deal, pull the 0.5 out the front. But this time, you'll notice that it's not a continuous pattern. See, f of 0 is in here twice. So you really need to watch out for that when you are doing these questions. So again, define the function, substitute in my x values, find the sum, and I've done it slightly differently this way. What have I done? I've done it two different ways here. So I have defined, let me just zoom in so you can see this. Come on. So the first way I've done it is that I've actually defined f of x and used f of x here. But you can do the same thing with the sum, and instead of having f of x, the only difference is I've actually got the formula or the expression. You don't put f of x is equal, you just put the expression, and that will work just as well. So for this one, this value here, the 15, is the sum, which is this bit. And so our final answer is going to be equal to 0.5 times by the 15 that we got from here as our sum. And so our area is 7.5 units square. And you can write it like that if you like. And finally, one with a little twist, and this is from a VCAR paper because you know VCAR does like a little twist in their questions. So this time you'll see that they've got the rectangles sitting horizontally instead of vertically. And so we'll need to work out our values for the heights of these rectangles using the same idea, but this time we're working with our y values. So I'll let you read the question and then have a think about how you would go about doing that. Okay, so we know that we need to find this length here, and that this length is our y value for this point, and our y value for this point is 4. And so we know the relationship from the line is y is equal to the square root of x, because they tell us up here and they tell us over here. So y is equal to 4 and y is equal to the square root of x. That means that 4 is equal to the square root of x. So this value here, to get x by itself, square both sides, and you have that x is equal to 16. So this is the point 16, 4. We do the same thing with the 3. So our y value for this point is 3, and 3 is equal to x squared, because that's the formula for this line. So that means that our x value that goes in here, this length here, is in fact 9. We do the same for the other 2 points, and our width for each of our rectangles is a 1. So the area of the red rectangle, if you like, is 16. The area of the green rectangle is 9. The yellow rectangle is 4. And the blue rectangle is 1. Correct answer is D.